Okay, now we're going to look at some more data. I understand that these concepts are a little confusing and they're new. Hopefully, looking at this sample set will help clarify some of them. Here what we have is a table of data points, and this is the results of doing an experiment. Remember, an experiment includes the tools used, the procedures followed, and the number of repetitions. In this case, we have 6. Now, for this table, I can actually change the number of data points, and I can also change the the experiment that was performed. So we can actually have up to 10,000 different experiments that are all identical. And we can then see how things vary randomly. Before we do that, what I want you to do is just calculate the mean, standard deviation, and standard error for this particular experiment. And we'll look at what the results are. So pull out your calculator and actually practice entering these numbers in and calculating the mean, standard error, and standard deviation. You've done that, we can click on this button right here and have the computer actually do the calculation for us. So for this particular data set, the mean value is 44.14. Standard deviation of these is 44.30, and then the standard error is 1.75. Now, to cite these correctly, we take the standard error and we round that off to 2 sig figs, which means 1.8. Since the second digit here is the tenths place, we round off the mean value to the tenths place. So the proper way to cite this is 44.1, rounding off to tenths place, plus or minus 1.8, which is our standard error. Now, what that means is if we were to reproduce this experiment over and over and over and over again, same procedure, same instruments, 6 trials, we would expect an average value that would follow a bell curve with a standard deviation of about 1.8. It's just to say the average value will vary, and it'll vary about plus or minus 1.8. Or about 2/3 of the results will be within plus or minus 1 standard error. We'd expect about 95% to be within 2 standard errors. So if we reproduce this over and over again, we would expect our average values to vary, and they'd vary by this 1.8. Here we can actually do that, because if I take this slider right here, this is the same as doing the exact same experiment, same number of data points, but just changing the random seed. So I change this right here, and we will notice that the mean value does change, the standard deviation does change, because that's based on the actual data, which you can see is changing, and the standard error changes. Notice what doesn't change. The tens place in the mean value. This is always 4, because notice our uncertainty falls in the units place, not in the tens place. So we're very confident that the true value is in fact 40 something. What we're uncertain about is the units place, and international convention is you cite 1 extra uncertainty. So it's always the last 2 digits that are uncertain. And we can see here, yes, the last 2 digits here are in fact uncertain when we reproduce the experiment over and over and over again. It's always 40 something, but the actual value right here does change. We can get 49, we can get 43, we can get 48, we can get 46, but it's always 40 something. These numbers, if we actually recorded all of them, all 10,000 of them, we could create a histogram. We'd expect that histogram, in fact, to be like a bell curve, and the width of that bell curve would be the standard deviation, and the standard deviation of the mean values would be the standard error. Now notice the standard error does itself change. In fact, it changes a fair amount because we only have 6 data points. But it's always something like 2. Ours is a little less than 2. Here it's a little more than 2. Sometimes it got as small as 1. And sometimes if you look carefully, I believe it does go up to, I just saw 3 there. So it does occasionally get much, much bigger. But the standard deviation, there it is, a 3. The standard error is something like a 2. So if we were to repeat this exact experiment 12 times, we'd expect the mean values here to vary randomly. And we'd expect, as I said, about 2/3 of them to fall within plus or minus 1 standard error, and about 95%, or almost all of them, to fall within plus or minus 2 standard errors. Notice if we were to take and change the experiment, change the number of repetitions we do, and change it from 6 to 24, or increase it by a factor of 4, what would we expect to have happen? Well, if we make more measurements, we'd expect we'd have a better chance of every value that's too large to be counterbalanced by a value that's too small, and to average those out and to get a better value for the mean. I would not expect my standard deviation to change that much because we're still using the same instrument, we're still following the same procedure. So our individual values will vary just as much. The difference is I would expect to have a better chance of having any value that's too big to be counterbalanced by a value that's too small, and to average out closer to the true value. So we can try that. We can take the number of data points right here and we can increase it. Notice the table gets bigger, we have more and more numbers. This is why we really want the computer to do the calculations for us. And I overshot it, so let's go down to 24. So here we've got, hopefully, 25, go down one more. We've got 24 data points. We have basically increased the number of samples by a factor of 4, and our standard error now should become smaller. So if we take and look at the different possible experiments here, notice now the standard error is generally speaking around 1. And it's varying a lot less because our mean value is going to be varying less. Notice here it's usually 44 or 45 or 46. Occasionally a bit more, occasionally a bit less. But generally speaking, the units value is changing but not as much. Now it's only changing by about 1 or so. So our standard error has gotten smaller. Our standard deviation is the same. It was about 5 before, and it's still about 5. So notice as we change the number of data points we measure, the standard deviation doesn't change by that terribly much because we're still using the exact same instruments with the exact same procedure. This doesn't change. The mean value becomes more consistent because our standard error gets smaller. If we were to increase the number of samples by a factor of 4, the standard error goes as the square root, so that should basically cut our standard error ideally by a factor of 2. So if you want to improve your precision by a factor of 10, that means you need 100 times more data points. If you want to increase it by a factor of 2, you need 4 times as much data points.